Hello friends, today I shall talk on Riemann hypothesis. I named the article as Towards Riemann hypothesis. So I will I'll state my talk introducing Riemann hypothesis, and it's one of the problem which will bring you $1 million US dollar if you can solve it. So it's a nice and quick pocket money for a math problem. So we start with a harmonic series 1 plus half plus 1/3 plus 1/4 plus 1/5, which we know doesn't converge, it diverges to infinity. A bit of history: harmonic sequences have had a certain popularity with architects. This was so particularly in the Baroque period when architects used them to establish the proportions of floor plans or elevations and to establish harmonic relationship between the both interior and exterior architectural details of churches and palaces. The fact that the harmonic series diverges was first proven in the 14th century by Nicole Oresme, but this achievement fell into obscurity. Proofs were given in 17th century by Pietro Mengoli, John Bernoulli and Jacob Bernoulli. The proof is easy. I can make this 1/3 to half and reduce the value. So this harmonic series is greater than 1 plus half plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/16, etc., which is nothing but 1 plus half plus half plus half, which is 1 plus 1 by 2 to the power n, which converges, which diverges, which goes to infinity, but in a very slow rate. So this is the general proof that harmonic series diverges. So next comes Bessel problem. When we talk about 1 by summation 1 by n square, 1 plus 2 square, 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square, which is proved to be pi square by 6 by Leonhard Euler. A bit of history. The Bessel problem was first posed by Pietro Mengoli in 1644 and solved by Leonhard Euler in 1734 and read on 5th December 1735 in the St. Petersburg Academy of Sciences. Since the problem has withstood the attacks of the leading mathematician of the day, Euler's solution brought him immediate fame when he was 25. So this is a significant work in the life of Euler. Euler generalized the problem considerably, and his ideas were taken up years later by Bernard Riemann in his seminal 1815 paper on the numbers of primes less than a given magnitude, in which he defined his zeta function and proved his basic properties. The problem is named after Bessel, hometown of Euler, as well as the Bernoulli family, who unsuccessfully attacked the problem. Euler's original derivation of the value pi square by 6 essentially extended observations about the finite polynomials, assumed that these same properties hold true for infinite series. 100 years, which was not rigorous. 100 years later, Carl Weierstrass proved that Euler's representation of sine function as an infinite product is valid by the Weierstrass factorization theorem. By simply obtaining the correct value, Euler was able to verify numerically against partial sums of the sequence. The agreement he observed gave him sufficient confidence to announce this result to the mathematical quantity. So Euler calculated the partial sums and then got the confidence. A bit of proof. So sin x is x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, etc. So sin x by x equal to 1 minus x squared by 3 factorial plus x4 by 5 factorial minus x6 by 7 factorial, etc. So sin x by x is 1 minus x by pi into 1 plus x by pi into 1 minus x by 2 pi into 1 plus x by 2 pi, which can be converted as 1 minus x square by pi square into 1 minus x square by 4 pi square plus into 1 minus x square by 9 pi square, etc., which is sin x by x. So equating coefficients of x square from both sides, we get summation 1 by n square equal to pi square by 6. This representation of sin x by x as an infinite sequence is an infinite product sequence was not rigorous, but Carl Weierstrass later proved it to be rigorous. Then coefficient of x to the power 4, x to the power 8. Equating the coefficients of x to the power 4 and x to the power 8, we get 1 by n to the power 4 equal to pi 4 by 90, 1 by n to the power 8 equal to pi 8 by 9840, etc. A natural extension for Euler is to define Zs, summation n equal to 1 to infinity 1 into n to the power s, for real s greater than 1. For s equal to 1, it diverges, we know. For 2, it is finite because it is pi square by 6, so I am not going through this proof. Now Euler connected the primes with this. Zs equal to 1 by n to the power, summation 1 by n to the power s, which is product over primes 1 minus p to the power minus s inverse. So that's the connection between Zs and the primes. To prove that, we can start with the sequence 1 by 1 minus x whole to the power 1 by 1 minus x, which is 1 plus x square plus x cube, and some product over the primes p 1 by 1 minus p to the power minus s whole to the power minus 1 is product over p summation k equal to 1 to infinity 1 by pks. Now if we interchange the sum and product, we get this relation. Now that connects 1 by summation 1 to the power s to primes, because here we have the prime factorization of the numbers and it's the sum and product over them, so we get all the numbers. There is an alternative proof using sieve of Aristotle's, which I am not going through, and it proves Zs equal to product over primes 1 by p to the power minus s whole to the power minus 1. Now comes Riemann. Despite the fundamental importance of Zs, Euler prefers to take this function and domesticate it and maybe make it do tricks, were hamstrung by the fact that it always seemed to be blowing up at s less than or equal to 1. As a result, he gave up and spent the remainder of his life going blind, working on other mathematics in dark attic. The function continued to lay prostrate in the useless state for over a half a century until Bernard Riemann came along. He took the function into his office, watched it self-destructively blow up any time in negative numbers when mentioned, and decided that it needed help. Although Riemann was not a number theorist by trade, he felt much like the guy in the movie Lorenzo Oil that could teach himself enough number theory to cure Zs of his horrible ailment. Riemann changes the symbol from Zs to Zetas. So there comes Riemann's function, Riemann hypothesis function Zetas. So if you consider eta s a different function, 1 minus 2 to the power minus s into 3 to the power minus s minus 4 to the power minus s plus 5 to the power minus s, this converges for s greater than 0. The proof is omitted. Now we can see that eta s is nothing but 1 minus 2 to the power 1 minus s zeta s. So zeta s equal to 1 minus 2 to the power 1 minus s inverse eta s, and get well defined for s greater than 0 except s equal to 1. So that's a stretching of eta. And now one can take it to complex plane and look at this analytic expansion, and we can see the trivial zeros from this formula suggested in 1749 by Euler. 1 minus s to the power 1 minus equal to the power 1 minus s pi to the power minus s sine of 1 minus s by 2 pi s minus 1 factorial zeta s. So if you see zeta 2n, so you put s equal to 1 plus 2n, this becomes n pi by 2, which is 0, sine n pi by 2. So for minus 2n, zeta is equal to 0, which are called the trivial zeros. There is another form. After months in his basement laboratory, Riemann emerged with a function that had the scientific importance of the Frankenstein monster and the aristocratic appeal of, well, the Frankenstein monster. They take a look at this. So this is the representation of zeta s for the whole of complex plane. Now if you look at the zeros, it was discovered zeta of half plus 14.1347 equal to 0, zeta at half plus 21.02 equal to 0, Hardy came up with the result in 1914 saying that zeta s has infinitely many zeros that with real part half. And Riemann hypothesis says that if zeta is equal to 0 then and s is not a negative even integer, then s equal to half plus it for some real number t. So everything falls on the real line half. So that's the Riemann hypothesis. I leave the proof or disproof of it as an exercise. And equivalence, I'm not going through it. It's a fact that Riemann hypothesis is true if px never differs from Lix by more than root x log x. Converse factor, if px has never differs from Lix by more than root log x, then the Riemann hypothesis is true. So this is a characterization of Riemann hypothesis. You can prove either of the problem to get $1 million. I'll stop here. Thank you.